I have to confess with some embarrassment that this is my first time at AGCT, but it certainly won't be the last. I'm very happy to see lots of familiar faces and lots of faces that are new to me. So for those who are familiar, you know, part of the story that I'm about to tell you is something that you've probably heard in various contexts before, so that part of the talk is not for you, and I hope that's okay. But I'm hoping to sort of do an introduction to sort of some ideas along the way to this topic of probabilistic approaches to rational points on algebraic surfaces. So let me get started. Okay, so I'm going to take x over q to be some geometrically rational surface. Let me just say briefly what I mean by this, and then I'll address why. So by nice, I mean smooth, projective, and geometrically integral. And by geometrically rational, I mean that if I fix some algebraic closure of Q and I base extend to that algebraic closure, then my X becomes actually isomorphic to P2. But that isomorphism is only visible perhaps over Q bar, but not necessarily over Q. Okay, so yeah.
Do you actually mean isomorphic or birational?
Sorry, birational. Sorry, yes, I mean birational. Yes, thank you. I mean birational to P2. Yes. Yeah. So in fact, the question is like, why do this? Okay, so before we even launch, like let's sort of pause to think about why this is a reasonable thing to do. So a lot of questions that we ask in arithmetic, sort of nice varieties, depend only on the birational type of the varieties. Their answers depend only on the birational type of the variety. And so I'm sort of picking dimension 2 as a place to work. There's lots of people who work on curves, and I'm sure we'll see lots of talks on curves this week. I like to work in dimension 2, and so I'm sort of looking at the simplest birational class of surfaces in dimension 2. And I want to study their arithmetic. Okay, so an example of this is nice surfaces that have ample anticanonical class. These are called del Pezzo surfaces. Their main sort of discrete invariant is their degree, which is the self-intersection of the canonical class. If you haven't seen these things before, this might not mean a whole lot, so let me actually give you some concrete examples. This number d is a number that ranges from 1 through 9, and it almost roughly gives you a sort of geometric classification of these surfaces. So let me show you what happens in low degree, because these are the interesting cases in terms of arithmetic. So del Pezzo surfaces of degree 4 are sort of smooth, complete intersections of two quadrics in 5 variables, so they live naturally in P4. Del Pezzo surfaces of degree 3 are cubic surfaces. Okay, so this is very classical objects. You know, it goes back to Cayley and Salmon and studying, you know, the 27 lines on a cubic surface. It's those cubic surfaces, but I'm going to look at them over the rational numbers and try to study their arithmetic. I've highlighted them in red because they're going to be the sort of the main subject of this talk. But I should also tell you that I'm really interested in what happens in this talk if I look at these other degrees. Okay, so there's del Pezzo surfaces of degree 2 are smooth quartics in a weighted projective space. So x, y, and z have weight 1 and w has weight 2. And so this f4 right there is some homogeneous polynomial in x, y, z. I can also think of this as a double cover of P2 that's branched along the curve f4 equals 0 on P2. And there's degree 1 surfaces which are smooth sextics, also in a weighted projective space, where x and y have weight 1. And the subscripts on the a and the b indicate the homogeneous degree of those polynomials. And z has weight 2 and w has weight 3. And this looks kind of remarkably like an elliptic curve over a function field where you have something like t, where t is like x over y, and that's not a coincidence. These things have a nice kind of elliptic vibration structure. So there's lots of things to look at. So these are concrete instances of geometrically rational surfaces, and like I said, I'm going to spend most of the time today on cubic surfaces. Okay, so let's go back. We started with some nice geometrically rational surface. Think a cubic surface. So it's going to be defined by some homogeneous polynomial of degree 3 in 4 variables. And the question, what we want to do is determine if there's some rational point on this thing, right? Is there some vector of solutions to my polynomial equation, all whose entries are in Q? And so famously, a necessary condition for this is that you have to have points over every completion of Q. So all the p-adic completions, but also the real numbers. This is what I mean by p equals infinity there. And because x is projective, I can sort of bundle up this nice product of p-adic points into the adelic points of my x. And that's really nice because it'll sort of compactify the notation a little bit. But we just need to think of this x of aq as sort of the set of local points on my surface. And so I'm just going to change my necessary condition to saying that x has to have some adelic point. Now, sadly, this condition isn't sufficient. So here's an example. This is due to Castles and Guy from 1966. It is historically nowhere near close the first example of a surface that has p-adic points and real points, but no rational points. There were many other examples of varieties before Castles and Guy found this particular example. This example has some sort of historical value. So I was once told that so Castles did a lot of numerical experiments for a while on these diagonal cubic surfaces, and he arranged the coefficients between like -5 and 5, and he found that they all did satisfy a local to global principle, and he started thinking that maybe they do satisfy the local to global principle. And so this example sort of laid that to rest. And it's not a coincidence. I mean, you need something special. So these numbers, 5, 9, 10, and 12, don't look particularly special, but if you look at the primes 2, 3, and 5, they each divide exactly 2 of these coefficients, okay? And that is actually what makes this a counterexample. More on that soon. So it's possible for these equations to have local solutions everywhere, but no global solution. And so you want to try to understand sort of mechanisms that can help you see why something like that can happen. Okay, so there's this mouthful. There's this thing called this Brouwer-Manin set. Okay, this is some set that is a subset of the adelic points that is carved out by what's called the Brouwer group of your surface. More on that soon. The important thing is that it's something that it can jam in between the set of global points and the set of local points. And I'm thinking of the set of global points embedded in the set of adelic points diagonally. Right? So remember, x of q includes into x of qp for every p, and so that's the sort of diagonal embedding that I'm putting in there. And so what can happen, and what does happen, for example, in the Castles-Guy cubic surface, is that you find that you have local points everywhere, but you can show that this intermediate set is empty. Okay? It's a computable thing, often. And so because this intermediate set is empty, that forces the set of rational points to be empty. That's great. Okay, but what's even better is that for the case of geometrically rational surfaces, there is a conjecture of Collet-Telen and Saint-Sucre that dates back to 1979, which says that basically this is it. This is sort of the only obstruction to the local to global principle that you ought to see on geometrically rational surfaces. Okay, so in the event that this mysterious intermediate set happens to be not empty, there ought to be a rational point. And so if you can get your hands on this intermediate set and prove that it is not empty, so that would give you a certificate that you have a rational point. Okay, it's conditional in this conjecture. There's been some progress. We seem to be a bit stuck right now. But the conjecture has since been generalized to rationally connected varieties. I am less sure that it is valid in sort of that generality, but for geometrically rational surfaces over Q, or over number fields, it seems quite reasonable, and it has stood the test of time for 45 years almost. Okay, so the point is that, you know, we're going to try to compute this intermediate set. And so I need to tell you a little bit, at least about the ingredients that go into computing this intermediate set. And I said something like, well, it uses the Brouwer group. It does. It uses this quotient of the Brouwer group. And if you haven't seen the Brouwer group before, I have really good news, which is that you won't need to know a whole lot about the Brouwer group today to understand what I'm saying. But I will tell you what it is. So it's the second italical homology with coefficients in GM for your variety, and you look at the torsion part. Our varieties are smooth, so it doesn't really matter, but that is the technical definition. Depending on how you grew up mathematically, you're either very happy or very frustrated by a definition like this. If you love to put things into computers, this is a really hard definition to work with. If you love to prove things, this is a great definition to work with. So you know, we need sort of tools that can sort of pass between sort of the theoretical way in which we think about Brouwer classes and sort of things that we can put in a computer. I'm quotienting out some subgroup of this thing, and this is the algebras that come from the ground field. So I have a structure morphism for my variety, X to spec Q, and this Brauer group is the second Étale cohomology. Cohomology is contravariant, so I get a map going the other way from the Brauer group of spec Q, which is just the Brauer group of Q, into the Brauer group of X. If you've looked at class field theory, the Brauer group of Q is absolutely enormous. And this image, this map from Brauer Q to Brauer X is often injective. Okay, so if you have local points, it'll be injective. And so this is an enormous part of the Brauer group, but it's a part that we're going to get rid of. We're going to quotient out by it, and we're not really going to care about it, okay, because it won't actually help in the construction of this obstruction set. Okay, so I told you that we didn't really need to know too much about the Brauer group, and the reason for that is that for geometrically irrational surfaces, there is a way of interpreting this quotient in terms of Galois cohomology. Okay, if there's some spectral sequence by Hochschild-Serre, where if you look at the long exact sequence of low degree terms, you can tease out an isomorphism between the quotient that we're interested in and some Galois cohomology group. In order to compute this Galois cohomology group, I need to understand the geometric Picard group of my surface, and I need to understand how Galois moves that geometric Picard group. If I know that, that's enough information that I can compute this H1 in a computer. Okay, so if I really have this concretely enough, I can just put in the action and press a button, and the computer will compute the H1. Okay, so that's already done for us. So this is really good. It means that instead of trying to understand this quotient, what we really need to understand is the geometric Picard group of our variety, and then how this Galois moves it around. Still, Galois of Q bar over Q is a bit of a scary object. It's, how are we going to put that into a computer? Well, the answer is we're not going to have to worry too much, because we're going to exchange Q bar for a finite extension of Q in a second. Okay, how are we going to do that? Well, let me remind you a bit about the geometry of cubic surfaces. So once I pass to my fixed algebraic closure of Q, it turns out that a cubic surface is isomorphic, and this time I do mean isomorphic, to a blow-up of P2 at 6 points. These points have to be in general position. That means no 3 in a line and no 6 on a conic for a cubic surface. And so, the Picard group of P2 starts out as Z, generated by the class of a line. And every time I blow up a point, I pick another Z direction. And 1 plus 6 is 7. And so the Picard group of a cubic surface looks like Z to the 7, at least as an abelian group. Okay? So I promised you that we would exchange Q bar for some finite extension, and we're about to do that. So remember that, these points, P1 through P6, are in Q bar, so they have some coordinates. These coordinates are algebraic numbers. There's finitely many coordinates. Adjoin all of those coordinates to Q, take some Galois closure, and now you have some nice finite Galois extension. And over that extension, this whole blow-up becomes visible now. You can sort of really sort of do this whole isomorphism over there. And so the point is that it ought to be that this Galois extension is really sort of already understanding all of the Galois action on the geometric Picard group, and that is correct. So if you have local points, which is an assumption that I'm making right now, but it's a reasonable assumption. Remember that I'm trying to determine if a cubic surface has a rational point. If it doesn't have local points, we can already go home. So we're going to sort of only look at cubic surfaces that have local points. In that case, when I take the Picard group of X base extended to that finite Galois extension, I always have an injection into the pick X bar fixed by the Galois group of Q bar over K, but that doesn't always have to be a surjection. But in the case that I have local points, I do have a surjection. And this isomorphism is in fact an isomorphism of Galois modules. And with a little care, that means that when you look at the inflation map in Étale cohomology, you get an isomorphism. And so originally, we were looking at the action of Galois of Q bar over Q on pick X bar. Now I only have to look at some finite Galois group acting on pick X after I base extend my surface to some finite Galois extension. Okay? This is really good news. So the reason is that if you want to understand this quotient, what we really need to understand is how this finite Galois group is acting on the Picard group base extended to this finite Galois extension. Okay, that sounds good, but you can say a little bit more. The Picard group was a Z7. It's an abelian group, but it's more than an abelian group. It has a bilinear form on it, so coming from intersections of curves on your surfaces, so there's a nice intersection pairing. And this Galois action actually respects that intersection pairing, and it fixes the canonical class, because the canonical class is defined over the ground field. And so that means that this action, you really get an action on the orthogonal complement of the canonical class inside the Picard group. And the fact that you have to respect this bilinear form means that my Galois action sort of is factoring through the orthogonal group of this lattice. Okay, so why are these factoids nice? There's a couple of reasons. So first, I already knew that this Galois extension is finite. This representation that I'm getting is in fact injective. And so since I have a finite group, I'm going to have some finite image. That's good. Okay. But in fact, it's not just a finite image. I can actually, because of this bilinear form structure that I have, I can actually say a lot about what kind of group this finite image has to be contained in. So Manin in the 1970s, at least that's the first written source that I know of. This might be historically an earlier discovery, but so he showed that this lattice, kx-perp, in fact carries a root system of type E6. Okay? This is actually not so difficult to show, but you need to know what a root system is and how to look for it. But the upshot of this observation of Manin's is that not only is this Galois group of k over q finite, but it lands in a subgroup of this orthogonal group that has to be a subgroup of the Weil group of this root system. Okay, we're not going to use root systems. I will use some factoids about this group, but the real point, okay, the message that I'm trying to get to you is that when you look at a cubic surface and you try to understand its 27 lines, and you try to see how Galois moves those 27 lines, the group that you're going to see is going to be a subgroup of this Weil group. And this Weil group has 51,840 elements. So it's not very small, but it's not too big. Okay? If you look at degree 2, in degree 2 you're going to see the Weil group of E7. That has about 3 million elements. That's bigger. And if you look at the Delpetzos of degree 1, you're going to see the Weil group of E8, and that has about 700 million elements. And that's a whole lot bigger. Okay? And so the ideas that I'll show you today, in part I'm choosing cubic surfaces because the numbers become reasonably small. But part of the idea is to really push this to degree 2 and degree 1, and also other kinds of algebraic surfaces. But this 51,840 is a little deceiving. We'll see soon that this is actually a product of large powers of small primes. And so it's a group with a ton of structure. Okay, so now we know that the Galois group that moves the 27 lines on a cubic surface is some subgroup of the Weil group of E6. And I know that the quotient of the Brauer group modulo constants is supposed to be some Galois cohomology that involves this image. And so Sooners and Dyer, back in 1993, did sort of just group cohomology calculation. He just said, okay, what if I let subgroups of the Weil group of E6 act on Z6, this kx-perp, and just compute all the Galois cohomologies that I can get. And, well, you actually get only 5 possibilities. You get 0, Z mod 2Z, the Klein 4 group, Z mod 3Z, or Z mod 3Z cross Z mod 3Z. So there's not a whole lot of possibilities for the Brauer group of a cubic surface. And in fact, let me make a couple of observations. One is, if your Galois group happens to be maximal, so if it's the whole Weil group of E6, then you get 0. And that happens for most cubic surfaces. Right? These Galois actions always want to be really big. Okay? If your Galois action is trivial, if your 27 lines are already defined over the ground field, this Galois group, this Brauer group is also 0. Okay, so to get non-zero Brauer group, you have to be in this very sweet spot between not too simple Galois action and not too complicated Galois action. Okay? So, but there are cubic surfaces that witness all of these groups. So all of these possibilities can actually happen for cubic surfaces over the rational numbers. So our goal for today is, remember that what we're trying to do is we're trying to determine if a cubic surface has rational points. There's a conjecture of Collet-Lennes and Souk that says that the Brauer group is controlling the existence of rational points on a cubic surface, and so we're going to try to compute the Brauer group at least to make progress towards that goal of trying to understand when cubic surfaces have rational points. Okay, now if you're sort of like, one of these people who love like deep cuts of like magma documentation, you will realize that this actually can already be done in magma. Okay, and so you might ask, okay, why bother? Well, okay, there's a few reasons. I'll give a couple sort of more serious reasons, but one is, and let me preface this by saying that I love magma, okay? So magma is great, okay? But there's a particular function called Picard-Galois module, and you feed it a cubic polynomial, and then it gives you the Galois module structure for this z to the 7. It's amazing, okay? It's not very fast sometimes. On a random cubic surface, it can take about 7 minutes. But there's no documentation for it. I mean, I found it by accident because I was looking at something else. And then, I tried looking everywhere, and there's sort of, no documentation. There's very little explanation of what's in there. And when I sort of inquired, I imagined that Stefan Elsenhans had actually programmed this, but it turns out that he had not. And so he thought that perhaps Steve Donnelly did it, but apparently Steve is no longer working in magma. And so it's like, wait, okay, so what is this function doing? I mean, we could try to find out, but this is sort of one of the disadvantages of having sort of closed source software with documentation that's not quite complete. And again, this is not per se a dig on magma. I really like magma, but sometimes you can have pitfalls like this. Okay, but the other reasons why we're doing this is that at the end of the day, cubic surfaces are a proof of concept case. There are other surfaces to try, and there are no magma commands, internals, that will help you for those surfaces. Okay? And second, and I think also very interesting, is that there's an existing method, so we can benchmark how these new ideas are going to be. Are they good? Are they bad? Well, we have a different way of doing it. It's good to have multiple ways of doing things. So in any case, I think it's still good to try to do this for cubic surfaces. So that's what we're going to try to do. Okay, so our job is we have to compute how Galois moves the 27 lines on a cubic surface. And so you might just think, well, I just have to compute the splitting field, right? If I can compute K, and I have the Galois group of K over Q, I can just, calculate my 27 lines and apply those elements and move the things around and then see what happens. And that would work. But the problem is that this is sort of the naive thing to do, to compute that splitting field. The number field might have very large degree. For example, if the Galois action is generic, that number field is going to have degree 51,840. And it might be really difficult to even just construct that number field. Okay? And especially if you're doing it blindly. If you had some specific surface where you can sort of see what's going on and very cleverly adjoin things in just the right order, you might be able to do it quickly. But if you need to do it in some sort of generic way, it can take a long time to calculate this thing. Yeah?
So your surfaces, are they explicitly given as a blown up of 6 points in the plane?
No. I am just giving them as a cubic equation. Thank you for that question. Yeah. So it's just as a cubic equation in P2. So
the Galois group can actually be bigger than S6.
Yes. Yeah.
The point is that those 6 points don't have to be a Galois order.
No, it's it.
Right. Yeah. Yeah. So what we're going to do is we're going to do reduction modulo P. Everybody loves reduction. So okay, so I'm going to start with a smooth cubic surface. There's this splitting field that I don't want to calculate, but I know it's there. I'm going to look at some prime of good reduction for x. And I'm going to look at a prime ideal above P. And if I do that, I have both my original representation and the representation of the reduced surface. It's a prime of good reduction, so when I reduce mod P, I also see a del Pezzo surface, a cubic surface, but it's going to be defined over Fp. Okay? And the idea is that once I work over finite fields, I have Frobenius. Frobenius is awesome. Okay? I have this sort of like canonical element out there that at least gives me some kind of conjugacy class in my original Galois group. And so the point is that when I look at the image of Frobenius, if I see how Frobenius is moving my kx perp in the reduced del Pezzo surface, then at least I get some kind, I can lift it to some conjugacy class on the image of my original representation. So out of reducing modulo p and seeing how Frobenius moves the 27 lines over fp, I get at least a little bit of information about the kind of elements that have to lie in my Galois group. And the idea is to try to do this for lots of primes. That's not a new idea, okay? But how we use that information, I hope you'll find interesting. So what we're going to do is we're going to start with a smooth cubic surface. We're going to reduce modulo lots of primes. And the word lots can be quantified, okay? So ideally, I would say that you should do it in batches of about 10 primes at a time. And if I don't get to that, someone please ask me at the end, why 10? And then we're going to compute, how Frobenius acts at each of these primes, and that's going to give us some conjugacy class in the image of rho x. And so we're going to get lots of these conjugacy classes. And our job, okay, and this is the hard bit, is from that information that we gather, how do we decide what the most likely subgroup of the Várilly group of E6 for our cubic surface is? Once we have that, we can compute this Galois cohomology group. This is sort of one line of code in Magma. Okay? So steps 1, 2, and 4 are actually quite easy to do. It's step 3. How do you decide, given the information that you have, that you can, pinpoint the subgroup, or at least the conjugacy class of the subgroup that you're looking for. Okay, so for that, let me just sort of look internally a little bit at the Várilly group of E6. It has large order, but this order was a product of small primes to high powers. The orders of the elements are not too big. That means that my Frobenius can't have very large order. That's good. The Várilly group of E6 has 25 conjugacy classes. That's not too many. But it does have 350 conjugacy classes of subgroups. And the Brouwer group will only matter, it will depend only on the conjugacy class of the subgroup of the image. And so I need to get my hands on 1 out of 350 possibilities. And these are the orders of the subgroups. So these are also the degrees of these number fields that you might be trying to construct. And so there's lots of very large numbers in there. So this is also why it's not such a great idea to try to construct that number field. If a priori you know that your number field is pretty low degree, then go for it and construct that K. It won't be so bad. Okay, so what we need is we have these 350 conjugacy classes of subgroups, and I need some kind of fingerprint for each subgroup. And so I'm going to call that fingerprint spectral profile. I like that name. It probably has a different name in the literature. I haven't found it yet, but that's my confession of not knowing enough group theory. But what we'll do is we'll grab each subgroup of the Várilly group of E6, and then I'll just go element by element of my subgroup and ask, what conjugacy class in the whole Várilly group of E6 does my element belong to? There are 25 conjugacy classes, so there are 25 buckets for me to put the elements of capital H in. And I just go element by element, and I put them in buckets. And so this numbering of the conjugacy classes is pretty standard by now. So Swinert and Dyer wrote some paper on cubic surfaces and wrote down the conjugacy classes in some order, and everybody seems to use this order now. And so that's the one we'll use. But here's an example of a particular group of order 48 inside the Várilly group of E6. And so the second row there, if you add those numbers, they add up to 48. And the spectral profile of my subgroup is just going to be take those numbers and divide by 48. So I get this vector with 25 entries, all fractional, and those fractions add up to 1 because I divided by 48. I've normalized this. And soon we're going to start thinking of these fractions as probabilities. Okay, so this is going to be my fingerprint for the subgroup. Unfortunately, okay, unlike in, as far as I know, and on Earth, where we each have our own fingerprint, not all the subgroups have different fingerprints, but it's close. So I told you there are 350 conjugacy classes of subgroups in the Várilly group of E6, but we only see 339 different fingerprints for these subgroups. There are 22 collisions. There are 11 pairs of subgroups that end up having the same spectral profile. The good news is that for 6 of those 11 pairs, Since we're only interested in the Brauer group of our surface, it won't matter, because for 6 of those pairs, the Brauer group that you calculate out of them is the same. So even though we might not be able to identify exactly which subgroup it is, the Brauer group will be the same, so we're good. So that leaves 5 pairs. Okay, so that's sort of 10 subgroups of my 350 that I may not be able to sort of use to compute the Brauer group of a cubic surface. But that does mean that there's 340 where I can work. And here's the best part of this news, is that of these 5 pairs, the Gala group, the largest Gala group that you'll see, has order 18. So the largest number field that you'll have to compute is degree 18, and that we really can do by hand. So if you see one of these collisions later, we can just actually compute the splitting field in the naive way, and it'll be really fast. In fact, it'll be faster than what I'm about to show you. So even though there's this wrinkle, we can sort of get over the problem. But I wanted to sort of point this out because it's important. Okay, so here's an example. This looks like a random cubic surface. It is not. It is in the Elsen-Hansiano database. Its Gala group actually has order 48, if I remember correctly. And 48 is much smaller than 51,840. Okay, so it's not apparent from the equation, but it is, that is what happens. Okay, so what we do is we're going to reduce this modulo 40 primes. So all the primes less than or equal to 197, but I throw out the primes of bad reduction for the surface. And I compute the conjugacy class in the Val group of E6 that I see when I look at Frobenius. And these are the numbers that I get. Okay, this is a real life example. And so the question is, I have 339 spectral profiles, and then I ask, well, given this data, which one is the most likely? Now, if you look at this data, this looks like a really small amount of data. This looks really poor, okay? But it is remarkable how good it is at actually figuring out what the spectral profile should be. So to do that, I need to take a very quick detour into Bayesian basics. So I hope you'll enjoy this example, because what we're doing is just a very slight generalization of this. Okay, so suppose that someone gives you a coin, and they tell you that the probability that it lands heads is 0.3, 0.4, or 0.5. But they don't tell you which one. They just say it's one of these 3. Okay? And so, well, you start doing an experiment, and you toss the coin 1,000 times, and it falls heads 482 times. And so then the question is, what's the most likely value for p? Who thinks it's 0.3? Anybody? Okay. 0.4? 0.5? Okay. Aha. See, we all have that Bayesian in us, right? The question is, how do we take that human intuition and put it into a computer, right? We all sense that, like, oh, for sure it's 0.5. Okay, but how do we do that? So we have 3 scenarios. So I'm going to take this vector of p and 1 minus p. P is the probability of heads, 1 minus p is the probability of tails. Notice I have 2 entries, they add up to 1. Okay, remember before we had a spectral profile, it had 25 entries and it added up to 1. Okay, so here I'm just simplifying it to have 2 entries so that we can see what's actually going on. Okay, so a priori I don't know which one of these things is. Before I run my experiment, all 3 possibilities seem equally likely. And so I'm just going to declare that the starting probabilities that it's scenario A, scenario B, or scenario C are all 1/3. Because I'm agnostic before I do the experiment. Then we do the experiment, and so we have this event. We observed 482 heads after 1,000 tosses. And so you can ask, well, what's the likelihood of observing 482 heads given that it was scenario A? Okay, and so this is just sort of some term computed from using a binomial model. And it's, as you can see, it's vanishingly small. And it's also really small for scenario B. It's also small for scenario C, but it is orders of magnitude better than the other 2. Okay, but these are not particularly big numbers. Okay, so what's going on? Well, we have asked for something really specific, right? We asked for 482 heads on the nose. We didn't give like a range of heads or something like this, right? And so we should expect that these numbers are really small. And also, these numbers are really sort of very independent of each other. These numbers do not try to put together the information that we know that A, B, or C are the only possibilities for my probability of heads and probability of tails. And so we can actually sort of compute what's called a posterior probability that takes that information into account. Okay, this is sort of like one of these, basic Bayesian rules. And so we can ask, what is the probability? So given the observations E that I have, what is the probability that it should be scenario A that's going on? Okay, and that uses the likelihoods that we have computed already, and so takes into account that information, that extra information, that only A, B, or C are possible. Okay, it's still a vanishingly small number, but I do it for B, and it's also a small number, and I do it for C, which is the one we thought it was, and now it's a very big number. And those numbers add up to 1. If you look at the fractions that are up there, and you add the 3 of them for A, B, and C, you'll see that it adds up to 1. Okay, and so this is sort of something that we could program into the computer, and then the computer will say, oh, I think it's C. Okay? You just tell the computer, like, do enough tosses until you reach a certain threshold for the largest posterior probability. And so that's exactly what we do in our example, right? But instead of having 2 states, heads and tails, we have 25 states. There are 25 conjugacy classes. Okay, so we can't quite use like the binomial model because there's more than 2 things, there's 25 things. So I'll just use a multinomial distribution instead. And so, now instead of having P and 1 minus P, I have my vector of 25 probabilities. This is sort of the spectral profile of the ith group. These probabilities add up to 1. I make my observations, and then I compute these posterior probabilities again. So, this likelihood was just like those binomial computations. Now I use a multinomial model. And then this posterior formula is just a straight up generalization of what we saw. There is nothing different here other than bookkeeping and a little bit more notation. But it's exactly the same as that coin toss experiment. Okay? This is a really, really basic idea. Okay? I'm not trying to do something particularly complicated, but I'm trying to apply this very simple idea to small amounts of data. And the cool thing is that this idea works. Okay? And so here's sort of a sample theorem. Okay, I'm going to choose some epsilon between 0 and 1, and I should say I never thought I would say that in a conference in my professional life as a mathematician. Let epsilon be greater than 0, but here we are. And so I'm going to take some cubic surface X, and I'm going to let SP be the correct spectral profile of the image of my Galois representation. I don't know which spectral profile that is. I'm just sort of labeling it. It's there. It's one of them. Let's call it SP. And what this theorem says is that if you make enough observations, and the number of observations depends on epsilon, then eventually the posterior probability of the correct spectral profile will exceed 1 minus epsilon. Okay, that's great. That means that if you make enough observations, eventually you'll be able to spot which one is the correct thing. Yeah?
That depends on your prior, right?
Yes, that's absolutely right. Okay, I also don't agree with my prior, but it's the best I have so far, but yes. Yeah, you're absolutely right. I'm using the prior of like all likely. Yeah, Kiran.
The other thing that's a little strange is you're treating each of the conjugacy classes as being equally likely?
Yeah. Well, no, I'm treating the spectral profiles, the entire spectral profile as being equally likely.
No, but your multinomial is,
Uh-huh.
oh, I see. So then the PIJs are sort of weight the classes according to their.
That's right. Those PIJs are the entries in the spectral profile which have the weights of the conjugacy classes built into them. That's right. Yeah. Yeah. So, and in fact, you can actually make this effective in the sense that you can calculate this X, okay? At least under GRH. You have to use the Chebotarev density theorem. I've spent a lot of time in the last few months doing this. It is unfortunate. The Chebotarev density theorem, the effective version, is sort of, it's awesome, but I think reality is even better. And so, so the x's that you get are very large. So sort of certifying with the effective Chebotarev density theorem, it can be done. And for cubic surfaces, it's actually not so bad. I mean, you might have to compute, in the order of millions of Frobenius. But that actually can be done. It'll take a few minutes, okay? But so it's not so terrible. But once you get larger groups like the value group of E7 and the value group of E8, it's going to be a bit more difficult. Yeah. Yes.
Calculation, are you
Right, I guess I was doing the former. So I should talk to you about this then. Yes. So, right. Good, so I want to do a little Magma demo, but just before I do that, I want to show you that. So Elsen, Enz, and Yannel have this database of 350 cubic surfaces, one for each of these conjugacy classes of subgroups. So we have this like nice ripe database on which we can test all of these ideas. And remember that out of these 350, you're only going to be able to tell what the Brauer group is for 340 of them. And you do this, and it works. For the entire database, it takes 184 seconds on my laptop. If I use the Magma internals, it takes 1,002 seconds. So these numbers actually hide something, which is that this sort of Bayesian idea is really bad when the Galois action is very small. Okay? But then the Magma internals are amazing when it's really small. And conversely, when the Galois action is really complicated, the Magma internals are horrific. And that's where the bulk of these 1,002 seconds are. Whereas in the Bayesian method, it's almost instantaneous. Okay, so, but a priori, you don't know which of these two camps you're in. So in some sense, what you should do is take your cubic surface and start running both of them at the same time. Okay? Okay, so let me show you what this looks like on Magma. So can you read this? Okay, great. So I'm loading some code. Okay, so here we go. All right, so I'm going to look at a random cubic surface. And I'm just going to do it in front of you and hope for the best. So in theory, if I pick a random cubic surface, it should be, the Galois action should be maximal, should be the whole value group of E6, and the Brauer group should be trivial. So let's see if we can do this. So I'm taking a random degree 3 polynomial with coefficients between -100 and 100. There it is. That's my random cubic surface. And now we're going to compute the Brauer group. Okay, so this C is this confidence. I want it to be 99% confident. We can set it higher if we want. Certification is false. So you might want to try to certify this thing. I don't want to do that right now. I just want to do the Bayesian calculation. And the step size is how many Frobeniae we collect at a time before we analyze the data. So I do that. Okay, 0.3 seconds. The Brauer group is trivial, indeed. And it says confidence is 1. Okay, when it says confidence is 1, it means it has a proof. Okay, why is that? Well, you see, here's the observed values of the conjugacy classes. And the only subgroup of the value group of E6 that intersects all the conjugacy classes that is observed is the value group of E6. So we have a proof. The Brauer group is trivial. 0.3 seconds. The Magma internals take about 7 minutes on one of these things. Yep.
Could you run it again?
Yes. Okay. But can we do it at the end? Because I don't know how to go back and then screw up the iLoad.
You can just delete and copy paste.
Wait, sorry. I'm happy to do it again, but maybe. So okay. So let's look at the Cassels-Guy example. So the Cassels-Guy example has one of these Brauer-Manin obstructions. The Brauer group is Z mod 3Z. Okay? That's not how Cassels and Guy did it. They used cubic reciprocity, which is the sort of internal structure of the Brauer-Manin obstruction for order 3 elements. Okay? So because the Brauer-Manin obstruction didn't exist in 1966. Manin defined it in 1970. Okay? So they had to do things kind of by hand. So there it is. I'm just going to make sure that it has registered F correctly because I'm using the same F. It's probably not good practice, but there we are. Okay, and so now it went to town. So it did a bunch of things. And it does say the Brauer group is 3. So that's Z mod 3Z. So it's calculated the correct Brauer group. You see these long lists? Those long lists are the posterior probabilities being calculated after every batch of 10 Frobeniae. The lists are not 339 long, because after it calculates a few Frobeniae, it can rule out a lot of spectral profiles. Because if you see a conjugacy class that has a 0 in your spectral profile, that spectral profile can't happen. And so I can also start ruling out a lot of things as I go along. And it looked at 90 Frobeniae. These are the observed values of my 25 conjugacy classes. I look at I divide by 90. And then it says that this spectral profile is the one that it thinks matches the best. And it took 1.24 seconds. So I can ask for more confidence, 0.9999, 99.99%. Same step size. Okay, and so it just takes a little longer, 2.4 seconds. But now you see, I mean, now that I have 140 Fabini, you really do start to see how the observed profile is getting closer to the actual spectral profile. This is not very much data, and it starts really sort of mirroring reality fast. Okay? So I'm going to use one from the Elsenhansianal database that I picked for no good reason, other than it worked nicely. And I only have so much time to do a demo, so okay, so that's the cubic surface that I'm taking from the database. I want 99% certainty. I don't want to certify yet. I want step size of 40. I compute. It's really fast. In fact, it needed 20 Fabini to pin down that the Brauer group is trivial in this case, and it is. So, I mean, I ran it through the whole database, and it always computed the correct Brauer group. Okay, but now you might want to certify it. Okay, so the only thing that this certificate is doing right now is that it's computing the order of the Gala group of that splitting field without computing the splitting field. Okay, you can do that. And so I'm just going to introduce that extra bit of information because that'll tell me what the first entry of the spectral profile has to be. Right, the first entry is the trivial conjugacy class. So the trivial conjugacy class is a 1 divided by the size of the group. So if I can calculate the size of the group, I know the first entry of my spectral profile. And so if I just add that extra little piece of information, okay, it's going to take a little longer because now it's calculating a Gala group, an abstract Gala group, but it works. Took 4.7 seconds. And you see it says the Gala group of splitting field of the Picard group has order 36. So with that one little extra piece of information, it was able to determine the correct spectral profile with proof, not just sort of some estimate. So here's another example, and I'm going to show it to you. This is the example that I showed you in the slides. I set the step size to 40 this time, so I would see 40 Fabini. And so this observed values that you see, that was the second row of that table that I showed you. And the confidence level is pretty high with just these 40 Fabini, and it doesn't take very long, less than a second. And I should say, I am not a particularly good programmer. Austin James, so a Rice PhD student with whom this is all joint work, is actually a very good programmer. But the code has sort of bits that she wrote and bits that I wrote. And the bits that she wrote are amazing. And the bits that I wrote, could probably yield some improvements. Okay, but now if I try to certify this one, it'll also compute the order of the Gala group this time, but you see it doesn't say the confidence level is 1. It actually gives you some non-1 answer. And if you look up, there's about halfway up there, there's an array with 2 entries, 1.0000 and then some really small number. So it means that it used this extra information of the Galois order, and it ruled out sort of all but 2 spectral profiles. And of course, internally we think, wait, I mean, with those probabilities, it's probably the one on the left, right? And I actually know how to resolve this now. I just ran out of time before coming here. I need a few more days of coding. So the certification here is coming. Yeah?
Is this a case where they just 2 groups of the same order, or they have the same Gaussian signature?
So they have the same order, and one spectral profile is like a subset of the other. That's the, yeah.
But what do you do when the spectral profiles are actually the same?
So in that case, the largest k that you ever see has degree 18, and so I just really do it by hand. So for the lower degree surfaces, we're going to have to do something different, because those number fields could actually have reasonably large degree. Yeah. And so and then finally, I want to show you an example of the rarest Brauer group, Z mod 3Z cross Z mod 3Z. So out of the 350 conjugacy classes of subgroups of the Val group of E6, only one of them produces a Z mod 3Z cross Z mod 3Z as the Brauer group. Okay? And this is in the 202nd entry in the Elsenhansianal database. So that's the cubic surface. I mean, these all kind of look the same. But they have really different arithmetic. Okay, and so here's the Brauer group. So it says Brauer group is Z mod 3Z cross Z mod 3Z, and 10 Frobeni was already enough to give me a 99% confidence level. So, can I prove this one?
Can the program prove it?
Oh, apparently, yeah. That was the next thing I was going to do. Okay? Yes. The answer is yes. The program can prove this one. Okay, so it knows what the size of the Galois group is. So, and you can see the Galois group of the splitting field has order 3. So it's a really, really small Galois group. And it produces sort of this crazy big Brauer group out of it. So, all right, so this is what I wanted to show you. So, you know, I know that I'm sort of doing something that's a little sacrilegious at first, which is that I'm sacrificing precision for speed, right, by sort of sampling a few Frobenius. But you really can certify these results. It'll take a lot of time. But the real point of doing something like this is now we can sort of do some really large-scale computation with cubic surfaces. And each of these Brauer groups won't take so long to compute. And if the Brauer group is 0, which is what happens most of the time, then you suspect that the local to global principle holds. And so, for example, we could like go try to check that, okay, on some big bunch of cubic surfaces. So, and that's just for cubic surfaces. We should do it for lower degree Del Pezzos. For some, you know, K3s of low Picard rank, we're only going to do the algebraic part of the Brauer group this way, but that's okay. We have to start somewhere. So in many ways, it's a sort of a collection of very simple ideas, but somehow it's quite powerful. It's much better, honestly, than anything I think we, you know, Austin and I could have hoped for when we looked at this. So, thank you.
Okay, we do have time for questions, but please do wait until the microphone is passed to you. So, start there.
Hi, this is a group theory question.
Oh no!
So, sorry.
Your chances just like pivot. Yeah, just yeah.
No, so
Okay.
you computed Frobenius and you saw which conjugacy class of elements you get to
Yes.
To figure out what potential subgroup there could be. But like if you look at Drew's subgroup signatures, if you keep track of some for elliptic curve images, like if you keep track of some additional information, you can actually point out which subgroup it is. Is there an analogous thing? Do you know what else you might be able to compute that will help you resolve these, whatever, 11 indeterminacies?
No, that's fine. Okay, I need to talk to you more about this. So
I don't know group theory either.
So what I'm doing is I'm sort of computing really fast the Fano scheme of lines, the 27 lines, as a set of points in a Grassmannian. And then I'm applying some random linear transformation, and then I'm projecting it all to one line. And so hopefully that'll be 27 points on that line. And then I'm going to compute, you know, then I get some like polynomial that defines that thing of degree 27, and I'll compute the Galois group of that polynomial. And that's how I'm getting the order. But that actually will also give you the correct Galois group. So if you look at how that Galois group starts operating on the lines, even just a little bit, that's what's going to sort of resolve some of the indeterminacy that I have. But that's sort of the naive idea that I've been trying that works surprisingly well so far. So.
I understand that your main goal is a challenged one for Del Pezzos of degrees 2 and 1, but may I ask you about another direction, say conic bundles with a large number of degenerate fibers, where you have W of dn, which also becomes larger and larger.
That's right, that's right. So thank you for that. That's awesome, yeah. I think that would be a really interesting direction to take this in. One thing that this method has one constraint, which is that in some sense you have to have this catalog of subgroups of the Weil group. And so for any particular value of n, you can do this. It would be really nice, in fact, to do it for like W of dn, you know. But that would definitely be sort of like a different level of challenge. But absolutely, for some specific value of n, where n is reasonably large, you could also do this and calculate the Brauer groups, I think. Yeah, thanks. Yeah.
Just a question about or a way you might optimize your prior. I mean, I could imagine, I would first try to rule out all the small guys that I can, and then take what's left that could possibly match, take the largest guys that are less that could possibly match the spectral sequence you've seen so far, and then I would be happy to take sort of a uniform probability over. I mean, I'm just wondering if that would improve, in your calculations of your confidences, are you actually including the fact that you've ruled out any place where you've got a non-zero
Yes.
entry? So
Yeah,
you're already including
and so it's sort of reuniformizing, those priors in the sense of, it's still sort of 1 over n, but n is changing as the number of distributions.
But you're still giving equal probability to ones that are small.
That's right.
Yeah.
That's right. So
Yeah, I could imagine optimizing.
Yeah, yeah. And one thing that one should also probably do is sort of you can feed the posterior probabilities as new priors for each batch of 10 things.
Yeah.
And I'm not doing that. I'm actually just sort of like starting from whole cloth. And even, it's still reasonably fast. I mean, I agree that,
Yeah,
maybe I can talk more to you about this.
You should just run it in a loop and update your priors each time.
Exactly, yeah.
So you were just saying about bigger groups that there's a problem of that you need this sort of complete table of what all the subgroups are.
Uh-huh.
But it seems that your method, you don't really care about the small groups, right? Because those as soon as you know that the group is small, you're going to switch over and do a Galois group computation.
That's right.
So is there a version of this where, say you know all the big subgroups, so to speak, which probably there aren't so many of them. The messiness is going to be down with the small subgroups.
Yeah.
So I don't know if enough computational group theory to know if this is feasible, but I think it should be possible to find the big subgroups and then have an undifferentiated pile of small subgroups. Is there a version of this method where you just plead ignorance as to what the small subgroups are? You just use the profiles of the big subgroups, and if it looks like you're not hitting any of those big subgroups, you expect that you get a small subgroup, and now you try doing Galois theory.
I think that's what will happen, is that if you ignore the small subgroups and you just run this naively, then these posterior probabilities will, it's hard for me to imagine that one of them is going to sort of start skyrocketing while all the others go down, but it's sort of going to be a mess. And as you see that mess, you can probably tell I'm in the small subgroup case. But yeah, no, that would be another really interesting thing to do.
Further questions?
Can I add one comment?
Yeah, I do
okay,
have
never mind.
one comment.
Yeah.
It's two actually. So one thing you could do to sort of see, if you want to challenge your probabilistic model, you could take an adversarial approach and take one of your examples and try and select how you can select devious primes so that you actually get, so you design your sample to get an erroneous prediction.
I see.
And then see how hard you have to work for that.
Yeah.
Probably pretty hard. But
Yeah, I can imagine.
The other one was when you were mentioning that you wanted to use this to test the local to global principle. How are you going to test it if it doesn't hold? If it were to not hold? How would you see that?
Well, if it were to not hold, and if you can prove that for that surface it doesn't seem to hold, then you'd have a counterexample to Collet-Tillenos and Sook's conjecture. That would be awesome. So I guess I just don't expect it to be false. But that's so. Yeah, it's definitely possible that the point of smallest height, for example, that the cubic surface has pretty large height, and so you're going to have to sort of, yeah. It's not a foolproof thing, but at least you can catalog which examples have the property that you can't seem to find a point yet, and either try to do something better and find a point in them, or start seeing if maybe they just don't have points. So, yeah.
Any further? Oh, so still. Yeah, okay.
Thank you. Hi, Tony. Thanks for the talk. I think I wanted to ask you, why do you need to test 10 primes at a time?
Thank you.
Right?
Thank you for that question. I really appreciate it. So the reason is there's something called the Chebotarev invariant of a finite group. Okay, and there's a very nice paper by Emanuel Kowalski and David Zuina on this. And what it says is, okay, so suppose that you have some finite group and you are holding in your hand some subgroup of it, which you suspect is the whole thing. Okay, so this is very similar to the kind of thing we're doing, where maybe we suspect it's the whole Val group of E6. So then the question is, how many how many samples do you have to take before you hit a set of conjugacy classes that are only compatible with the whole group. And for the value group of E6, the average number that you have to hit is 5, and the standard deviation is 2. And so that's sort of 2.5 standard deviations above the mean. And so it's pretty likely, if I take 10 Frobeni, and the value group is the value group is the value group of E6, that it will actually give you a proof. So that's why 10 for cubic surfaces. If I probably 11 would be even better, 3 standard deviations. But then the numbers that you get have denominators of some multiple of 11, and they're just messy. So and so for aesthetics, I did 10. But yeah, but there was sort of a reason to do 10. Yeah.
Okay, let us thank Tony again.